Last time we started in section 3.4 and we're looking at multiplication of whole numbers. And we had looked at some models of multiplication, like kind of what types of problems could come out of a problem requiring multiplication. And we're actually going to take what kind of feels like a little bit of a deviation, but it's the right location of it. We're going to talk about properties of exponents next. So let me get there. First, a definition of exponent. If you have a number a, and it is multiplied together n times, so this is n of these, so a to the power of n is defined as that for a rational number a. So a is actually any rational number. We are working in the whole number section, so that's what we're going to see most of, but we might see some fractions and such, but they work the same way. The base is called, the a is called the base, and the natural number n is actually called the exponent. So the first thing we're going to do is I'm going to define what the properties are, and then I'm going to justify for you why the properties work. I'm not doing that because I'm going to ask you later to justify it for me. That's not the point. Those of you who've taken proportional and statistical, we do this again in there, but we have more properties, so this is going to seem like a little bit of a review. But it's more to establish the why it works, because undoubtedly somewhere along the way, whether it's this topic or someone else, some other topic, some child's going to say, but why? Right? And it's really frustrating when that happens, especially when you have absolutely no idea why. And so at least having seen it in class here for this topic, and when they come across our paths, I'll mention them along the way, it gives you a reference point to know that you've seen it before and you can go figure out what it was again, because it's not the first time they're looking into it. So properties of exponents. We only have 4 in chapter 3 that we're looking at. We revisit the same topic again in chapter, I can't remember if it's 6 or 7 inside of proportional and statistical reasoning. So if you haven't been in that class yet, you'll have the chance to revisit this again as well. With a few more properties. But the first one is actually same base. Notice they all have the same base, a to the m times a to the n. These match. And when that happens, that actually yields the addition of the exponents. And it doesn't matter what the exponents are. We're specifically looking at exponents that are natural numbers. Okay, so like 1, 2, 3, 4, and so forth. The second one is division. The first one was multiplication of a to a power, and the second one's division of a to the power. So if multiplication becomes addition, what do you suppose division becomes? Subtraction, right. So this is a to the m minus n. And again, I'm going to justify for you why it does. But this is the property. The third one looks kind of like the first one. We have 2 exponents, m and n. They're both on a, but they're on the same a. They're not on separate, different a's. They're multiplied. So when we have a power raised to a power like this, we actually end up multiplying the powers, or the exponents. Okay. And the last one is sort of like a distributive property for exponents that exists. It only exists when the a and the b are multiplied, right? It has to be a times b that's raised to the power m. It can't be like a plus b. That doesn't work. So what happens is we just raise each individual component to the power of m. So it looks like what we're doing is taking this m and sort of dispersing it inside. Okay, are we good so far? Okay, so the next, I think it's 2 slides rather, where I'm explaining them are not something that I'm going to ask you to repeat, right? They're just for your information for future reference should you need to encounter them again. After that, we're going to take these 4 properties at face value and we're going to use them the way that you would be using them, without having to establish why it works again. We'll have established that already. All right, so the first one we said was supposed to be the addition of exponents. This is what it's supposed to be, right? A to the m plus n. So here's some of these, well, in fact, I think all of these today are going to be just examples showing you how they work. They're not really proofs. A proof means it has to work for any value, and I'm going to very specifically give you a number which therefore makes it an example, not a proof, because I'm giving a case. So we're going to look at a cubed times a squared. So this is an example only. So what does it mean to say a cubed?
A times A times A.
Right. A times A times A, three of them, right? And what does it mean to say a squared?
A times
If you count those up, how many do you have?
A.
5. So I have a to the 5th. And how do we get from 3 and 2 to 5? You add them. Right? So it's not a proof by example, but at least it's a justification by example. You can see how it's working for you. And this is really what you would do if you were asked this by a child, right? You'd say, well, take a look at this example. See how it's working. See why oh, look, it adds together. It's going to do that all the time. That's what you'd do. All right, so the next one is supposed to be subtraction. So again, an example. And the example we're going to use is actually going to have a to the 4th over a to the 1st, like that. All right, so a to the 4th means what? 4 a's. A times A times A times A. And I just have a to the 1st, which is just a in the denominator. These are all multiplied together. I mean, we don't put the dot a lot of times when it's just variables or, like letters, but they are multiplied together. And so what can we do with the a on the top and the a on the bottom? Yeah, we reduce them. Looks like cancellation. So I'm left with how many a's on top? 3. And again, how do you get from 4 and 1 to 3? You subtract. Yeah. All right, a couple more. This one was supposed to be multiplication, like that. And we're going to use kind of what looks like the same first one that we did before, where we've got a 3 and a 2 in it. So a cubed means I have 3 a's. And then squaring that means I have to do the 3 a's 2 times. And the grand total gives me how many a's? 6. And what do I do to get from 3 and 2 to 6? Multiply. All right. And then the last one says I should be able to distribute the m through to the a and the b. And we're going to do this with just a power of 3. So power of 3 means that I multiply something by itself 3 times. So I've got AB, AB, and AB. So far, so good? Okay, so do you remember earlier, as in like the very end of class last time, we established some properties for multiplication? And some of those properties said we can change the order of things, commutative. And other properties said we can regroup parentheses around more desirable pieces, right? And as we do those kind of regroupings in those ways, the commutative and the associative property, we are able to change this to have all the a's beside each other and all the b's beside each other. And we notice when we do that there are 3 a's, of course, and 3 b's. And we see that property displayed with a 3 as an exponent. Okay, so far so good? Okay. So we're going to be now using the properties of exponents with bases. One of the things to remember, again, about properties 1 and 2 is that the bases had to match. So when we look at example A, right on number 4, the 5s are all the bases and they match, but on B, something weird is going on that we're going to have to sort of change, right? It's a 6, a 2, and a 3, they don't match. And we can't just decide 6 times 2 times 3 and then do something with it. It doesn't work like that either. So let's start with the one that's pretty straightforward, which is part A. They all match. Now there's 3 of them here, but it's still really just property number 1, but with 3 things. So what are we going to do with those exponents? Add them all together. So we're going to take, and you don't have to write it out this way, but I will just so that you've seen it once at least. 10 plus 2 plus 4, and 5 to the 10 plus 2 plus 4 would be 5 to the 16th. Every now and then I have somebody ask me, but don't I need to multiply the 5s together? you are multiplying the 5's together. It's just taking effect in the exponent instead of adding the base in the base location. So you are multiplying them together. Now, on the next one, there's two different ways you can handle it, and they're both equally good. One way you can handle it is that you can break the number 6 apart. So how does 6 break apart if you factor it? 2 and 3, right? 2 times 3 is 6. So if we think about it like that, this would be 2 times 3 to the power 4 times 2 cubed times 3 cubed. And then what do you suppose we can do with this power 4? Yeah, we can distribute it. So I'm not going to have a single base, but I do have some matching bases now. I have 2 to the 4th, 3 to the 4th, 2 to the 3rd, and 3 to the 3rd. So they don't all match, but some of them do. So I can talk about just the ones that do, base 2 ones. So the base 2's, what will I do with your exponents? Add them. And the base 3's? Add them. So this is one option for an answer. Okay, one answer. Let me show you another way to do the problem that's a little different, that gives you an equally good answer. Instead of breaking the 6 apart, what we could do is we could recognize that the 2 and the 3 after the 6 both have the same exponent, the 3. So instead of distributing, like we did with our power 4, we could undistribute. It's called factoring. And we could write it like this. So we're really using property number 4 in reverse. Yeah? It's backwards. We're starting with what's on the right-hand side of property number 4, and we're merging it back into the left-hand side version. But equalities are able to do that. You can go either direction. So the reason that that's helpful is because what's 2 times 3? 6. Now they have the same base. There is only one base now in this one. So this would be 6 to the 7th. So either of these answers are acceptable. There are reasons why we might like one better than the other in a certain situation. The first one has the benefit that the 2 and the 3 are prime numbers. So it's in prime factorization form, something we'll talk more about in chapter 4. The second one has the feature that it's a single base. That's also appealing. So it kind of depends on what the goal is, and either one works for what we're doing now. Rylan?
Is the 2 to the 7th times 3 to the 7th simplified then?
Yes, it's in simplified form because it depends on what you mean by simplified. Does simplified mean broken down all the way or condensed all the way? It just depends. And so either one would be considered acceptable for what we're working with. Yeah. Okay, any other questions on that? Okay, we're going to move back into things that are not exponents now and take a look at some algorithms for multiplication. So there are several different ways that you can multiply. You guys are kind of on the cusp of when this started happening inside of what would have been your 3rd grade, 4th grade classrooms on this. You might have seen some of these things. You also very likely might not have. It just depends on where you went to school and what curriculums they were using at the time. But what I can tell you is that these curriculums are in play now, and they are being utilized all over the place. You are not going to be able to get away with teaching everybody how to multiply or add or subtract or any of the other things the way that it was done when I was a child. You're not going to be able to do that because the curriculums have changed. There are some really nice features about these as well. Sometimes it feels like, why did they make it more complicated? I know that when my husband looks at some of these things, that's his feeling. He's like, why didn't they just do it like they always did it? Well, the real answer to that question is because it didn't always work for everybody. And so the goal that I have is that you understand how to utilize these so that when you have those children, even if your curriculum doesn't specifically mention these, you have another option for teaching them how to do something, okay? So the first thing we're going to look at is what's called expanded form for multiplication. And we looked at expanded form when we did some addition, subtraction stuff, so part of this is going to feel a little familiar. Expanded form means taking the 48 and breaking it apart by place value. So you have a 40 and an 8. You have a 30 and a 2. That's what expanded form means. And so what we're doing is we're going to do the 40 plus 8 times 30 plus 2. And we're still going to multiply, and it's going to feel a little bit like our standard algorithm, but what it does is it pays more attention to place value. Okay? So we're going to take our 2 and we're going to multiply by our 8. So what is 2 times 8?
16.
16. So actually, well, it doesn't really matter what order. Let me actually start differently. We'll come back to the 2 times 8 in a second. We can actually move from left to right on this one. Let me do that one first. What we're doing is we're taking the number 40 and we're going to multiply it by the 30. So we're kind of going to go down in each direction. And then we're going to multiply it by the 2. I'm just going to write them all out. And then we're going to do the same thing with the 8. We're going to take the 8, and we're going to multiply it by the 30 and the 2. Okay, so far so good. They do not have to be written all linearly like this, left to right, like horizontal. If you want to write them stacked on top of each other, you could do that. To do the addition differently, that would be fine. We do need to multiply all 4 of these pieces together, though. So 40 times 30 would be the 12, and then the 2 zeros makes 1,200. What would 40 times 2 be? 80. How about 8 times 30? 240. And then my last one, 8 times 2 that I tried to do earlier, 16. And then we would add them all together to get our final results. And that actually ends up giving me 1536. Whether you do it left to right or top to bottom. The next example is actually like a more structured way of doing this same thing. This one is probably my favorite. This one has you take your 48 and write the broken down pieces 40 and 8 on the top. And on the left. I'm sorry, right. The right direction, the right-hand side. Yeah. All right, so I've got 48 on top, 32 on the right. And what we do is we break apart the square into rows and columns. So because we're doing a 2-digit by 2-digit number, we get a 4 square, right? If we had a 3-digit number by 2-digit number, we'd end up with 6 little squares in the middle. 3 by 3 would end up 9 squares. You can do it as big as you need to, and it will work on all the cases. But what you're doing is you're multiplying the row times the column, right? So the spot where I'm looking at my top left-hand corner has to be 40 times 30, because that's in that row and that column. So it's the same values that I got just a moment ago, but it's drawn in a rectangle form. So I have 1,200 here. I have that 240 here. 40 times 2 is my 80 on the bottom left. And 8 times 2 is my 16. Okay, is that good? And then again, we're adding all those together. So you add the sum up on the inside. So we add these all together. And my sum inside is the same 1536 as before. Here's why I like this. This actually has the ability to be shown in a visual sense that shows what you're doing. Now, it's done in a condensed form here, but let me draw it out in a bigger form so you can see what's actually happening. So what's actually happening here is something like this. It's an area model. This is 40, and this is 8. And this is 30, and this is 2. And the 40 and the 30 become 1,200, and you can look at that and say, yeah, it's a lot bigger than the other 2 values, right? The other 3. And you can say, hey, look, your 8 times your 30, that 240 is this narrow kind of piece. It's not as big as a 1,200, but it's the next biggest. I've got my 80 down here, and then I've got this tiny little bit, comparatively, and my scale, of course, is still a little bit off. But you have the sense of what's actually happening because of the sizes that are present there. So this one's my favorite because of the appeal to a visual. I'm a visual learner myself, and so I like this one. Interestingly enough, I taught lattice multiplication in my contemporary math classes this morning. So if any of you have friends who are taking contemporary math, they actually saw me do a lattice example from the next one. My daughter, who is really good at math, and she's always been pretty good at math, really struggled to learn to multiply with a standard algorithm. It just didn't click. I don't know why, but she didn't like it. And I showed her this partial products one because that's the one I like, and that really didn't do much better for her. But when I showed her lattice multiplication, everything clicked. And the reality is she can multiply with a standard algorithm just fine now. I mean, like, all that's fine now, but it took something else to finally get it all to click together, and this is what it was for her. So here's the way lattice multiplication looks. Instead of breaking the 48 into 40 and 8, we just write it as a 4 and an 8. So we're doing the single digits. And we're doing the 32 as a 3 and a 2. And we're still drawing a box, much like partial products, and making our grid 2 by 2. So all of that matches. Here's where it changes. Inside of my grid, I'm going to divide each of my boxes diagonally, like this. And what I'm going to do is just like what I did over here, I'm multiplying the row by the column. I mean, that's still happening. So I'm still looking at this 4 times this 3. The difference and why this is so friendly, there's several reasons, but one of them is because it's all single multiplication, right? So if your kids actually learned their multiplication facts, like they memorized it, this is very straightforward because it's just single digit times single digit, and that's really friendly. So the number 12 comes up when we get 4 times 3. The 1 goes in the top corner, and the 2 goes in the bottom corner. 8 times 3 is 24. So we did 2 in the top corner and 4 in the bottom corner. 4 times 2 is 8. It's just a single digit number, so it just goes in the bottom corner. And the last one is 8 times 2, which is 16. So I have a 1 in the top and a 6 in the bottom. So another nice thing that this does is it isolates all the multiplication in a single step. That happens over here too. First we do all of our multiplication, then we do all of our addition. And it happened over here too. First we do all of our multiplication, and then we do all of our addition. A standard algorithm doesn't do that. It mixes them in together at the same time, which makes it challenging when you're first learning. So first we've done all of our multiplication. Next thing we're going to do is we're going to extend the diagonals. However many diagonals you would have on your problem, you extend them. And you start in the bottom right-hand corner. And it's always a single digit, right? So it's a 6. What we're going to do is we're going to add along our diagonals, and these pieces have nothing to do with it. Okay, so don't go adding those pieces in. Those were the multiplication pieces, right? The factors of the multiplication. We're adding the sums. So when we add along diagonals like this, only inside the box. The second diagonal has 4 plus 1 plus 8. What does that add to? 13. We write our 3 down, and then we carry the 1 for the 13, right? We regroup. Our next diagonal has a 1, 2, and 2, which gives me a 5. And then our last diagonal in the top corner is a 1. And the answer, which we've now gotten several ways, is again 1536. Now, in any of these methods, can you check to make sure your answer's right? Of course you can. You know how to multiply that you did before, whatever it was you learned. And you've got your calculator, and it can confirm it for you too. So you should know when you get done whether or not your answer is correct. And if it's not, then you've got a flaw in what you've done in the method, and it's time to go back and reanalyze that. Any questions? Okay. So let me actually mention, before we move on to the mental math section, I'll actually write it out so you can see why I was highlighting it verbally the way that I was. The reason that the standard algorithm can be difficult for kids is because there's so many steps going on in a single step. So when I do 8 times 2 here and I get 16, I write a 6 down below and I write a 1 up above. Okay, so that's the first thing, is I've got to carry the 1 in the middle of what's going on. Then I multiply at a diagonal, right? So now I'm multiplying this direction. I've changed directions of multiplication. 2 times 4 is 8, but in the middle of my multiplying, I have to add a 1, which makes a 9. Whoops. Now, to further complicate the issue, this mysterious 0 just shows up out of nowhere. I have not seen very many people explain very much why that happens. It happens because the next number I'm multiplying isn't really 3, it's 30. Right? It's a 3 in the tens place. That's why that 0 is showing up. But it's a little mysterious looking. So the 3 gets multiplied now, and the 3 has to be multiplied by the 8, giving me a 24. But you got to remember that the 1 that was up there isn't really up there anymore, right? So now we got to like mark it out. And now you got a 2 up there. And when you're all said and done, let's see, 3 times 2 is 12, plus my 2 would be 14. We have to add again. All right? It's actually very efficient. That's actually one of the reasons why it's stuck around so much, right, is because you can do it pretty quickly. Once you get in the hang of it, it's great. But it lacks a little bit in its sort of smoothness, in its isolated operations, all those kinds of things. So don't just think, but my way was easy. Why would I keep doing it that way? Well, because your kids might need something different. Okay, so let's look at some mental math stuff. So we have 3 different types of mental math problems we're going to look at, or at least strategies. Remember, when we talk about mental math, we're finding exact answers. Jot that down if you haven't somewhere, if you don't have it somewhere already. Mental math means we're finding exact answers. The last number on your last problem on your sheet says computational estimation. Estimation is when we do approximations or rounding or something like that. We don't get an exact, okay? But mental math means we're doing it in our head, but we're still getting the correct answer, 100% correct. Okay, so front-end multiplying has to do with taking like a 2-digit number, 46 here, and breaking it apart so that we can multiply each of its digits individually by the 5. So remember, we had talked about mental math probably back in 3.2 was the first time we talked about it, and I said 3 steps. If you can't do it in 3 steps, it's not really considered mental math. And you're going to write them down simply because I can see them, but it should be simple enough steps you could do in your head. I think you can break 46 into the 40 and the 6. And what you're doing then is you're multiplying each of these individually by 5. Okay, so we're going to multiply 40 times 5, and we're going to multiply 6 times 5. So what is 40 times 5? 200. And what is 6 times 5? 30. And if I add them together, I get 230. So this is step 1, step 2, and then the addition of them would be step 3. Okay, so obviously this method is very limited. It's like 2-digit by 1-digit multiplication. If you had a 2-digit by 2-digit, it'd have too many steps. It would be more than 3, right? So keep that in mind. We're looking at things that are smaller types of numbers in order to do this one called front-end multiplying. All right, the next one, you'll notice compatible numbers has several numbers being multiplied. It doesn't look like the last one at all. There's no 2-digit numbers, but the key here is that it's lots of multiplication steps. And so what we're wanting is we're wanting to multiply numbers that are convenient to multiply together. And in particular, convenient means they turn into multiples of 10. So are there any 2 numbers you can multiply and get a multiple of 10? All right, 8 times 5 would be 1. And 4 times 5 would be another. Or if you wish, you can do your 5 times your 2. There's actually a couple ways you could do this one. So if you want to do 5 times 2, go for it. Okay. So I've already got this highlighted at this point, so I'm going to stick with this one now. So we're going to go with that. So we would take the 4 and we would rewrite it. 8 times 5 is 40. And then 5 times 2 is 10. Okay, so we're coming across nicer numbers than we had before, and fewer of them too, obviously. 4 times 10 is, I didn't say that right. 4 times 40 is what I want. I'm moving left to right at this point now. You could go the way if you want to, but 4 times 40 is, 160. I'm writing down a few extras here just to make sure we see them. And then 160 times 10 would give you 1,600. So the only time compatible numbers is going to come into play is when it ends up giving you things that multiply together to give you multiples of 10, right? Like the 10 here, or the 40, or if we had done 5 times the 5 times the 4, the 20 would have been fine. Any of those being multiplied would have been convenient. The last one is the one everybody always forgets. Highlight it, star it, I don't know. Every time I ask questions, people are like, what's that other strategy? They never remember this one. Thinking money is really very cool. I know you probably don't use cash as much as your parents probably use cash or something like that. I mean, like I realize that swiping a card's pretty convenient. I get that. But you have some sense of what coins are. And there are certain numbers that correlate to our coins. In particular, a 5 correlates to what coin? This is a nickel. So what this is equivalent to, because it's a 5, this is very specific, right? And you can't just have a random number, like 6 doesn't work here. It's 5 because it's a nickel, is that I have 46 nickels. Now, nickels are fine, but dimes are easier. If I have 46 nickels, how many dimes is that? 23. But what does 23 dimes mean? Well, it means 23 times 10. And multiplying by 10 is easier than multiplying by 5. 23 times 10 is 230, thank you. 230. Now, it works for all numbers. There's nothing special about it being nickels and dimes. So if you take two numbers, let me just make something up random that's similar, but it doesn't have coins with it. Okay, that's fine. I was afraid my little recording thing was stopped and it wasn't going to start again, but it did. It's good. Okay, so if you had something like, we'll see if I can make something up that works. 432 times 6, I don't know why I chose that, but that'll work. If you take the 6 and break it apart, you recognize, oh, it's 2 times 3, then you actually can always multiply and divide by the same value. So instead you could say, okay, well, I'm going to divide this one, actually let me do multiply. I'm going to multiply this one by 2, and I'm going to divide this one by 2. You can do that. That's essentially what I just did in our problem. We just did it with nickels and dimes. So you always have the ability to do that in a problem. You're multiplying two numbers. You compensate by multiplying one, dividing the other. It's just that it has this very nice visual connotation with the coins, with our nickels. Okay? The other one that's nice is 25. Because what is 25?
Quarter.
It's a quarter. Everybody forgets this one. This is a quarter. So this problem, 44 times 25, is equivalent to having 44 quarters. But in the same sense that dimes are easier to work with than nickels, what are easier to work with than quarters? Dollars. Much easier. And if you had 44 quarters, how many dollars is that? 11, right? What we're essentially doing is we're multiplying the quarters by, or we're dividing the quarters by, no, I said it right the first time, by 4. We're dividing our 44 by 4, and we're multiplying the quarters by 4. We're dividing one, we're multiplying the other. So this is 11, and then dollars is equivalent to having 100 cents. Right? That's what a dollar is compared to 25 cents would be a quarter. And what is 11 times 100? Yeah, 1100. And let me write out what I had said because I don't think I spoke it very clearly. Essentially what we're doing with my 44 and my 25 is we're dividing 44 by 4 and we're multiplying 25 by 4. So the 25 multiplied by 4 gives me the nice even 100, and the 44 divided gives me the nice even 11. And again, these are only nice because of the values that we happen to be working with. Okay, any questions? All right, our last example is a computational estimation. Okay, computational estimation means we're not going to get an exact answer, right? That's the goal. So what we're going to do is called front-end estimation. Now, if you'll notice at the very top of your page, there was a mental math process called front-end multiplying. Well, they got to be somewhat similar or they wouldn't have the same phrase front-end with them, right? So for front-end estimation, what it means is that I'm simply going to multiply the two first values in their place values respectively by the 4. So instead of multiplying 300 by 4, 80 by 4, and 6 by 4, I just do the first two digits. And it doesn't matter how many digits I had. If I had a 6-digit number, I'd just multiply the first two digits in their place values by the following value, 4. So what happens is I have the 300 times 4 and the 80 times 4. Well, let me put them to the side. What is 300 times 4? 1,200. And what is 80 times 4?
320.
320. And if I add these together, what do I get?
1520.
1520. And it's an approximation for the original value I was given, not an approximation for 1,200 and 320, but it approximately is what you would get if you have 386 times 4. Okay? So again, it doesn't matter how big the number is. If I had the number 426,297 and I wanted to multiply it by 6, all I would do is to take the first two digits in their place values times 6. So it would be, 400,000 times 6, and I would have 20,000 times 6, and then we'd add them together. It's just always the first two digits. Rylan?
Does this only work if one of the digits is single?
It would only work if one of the digits was single. Or it would work if one was nice. I mean, I suppose a 10 would be nice, but then we probably wouldn't be estimating because you could find it easily. So in theory, that would also work. But, yeah. Any questions on that?